Hello and welcome back to What Exactly. In this video, we are going to discuss about transformer networks. We'll be understanding the basic intuition behind transformer networks and why we are using transformer networks. Before getting started, let us understand why have we switched to transformer networks. In the previous RNN, GRU and LSTMs, our data was sequential. So if you are considering an RNN or GRU or LSTM, your data processed sequentially. Suppose you are having 10 inputs. So in order to calculate the output at 10th time step, you need to compute the output of 9 different time steps before 10th one. Like suppose you are giving X. It goes through the RNN cell, it will predict the next output and it goes sequentially. And if you want to get the 10th, only 10th output, if you are interested only in the 10th output, you need to compute these things prior to this. So this is the main disadvantage of RNN. And the other disadvantage is it takes longer time and it acts as bottleneck. So what is bottleneck? See, the information which you are passing to the further layers is not sufficient to predict the output. Like if this is 100th sentence or 100th word, the information which is at first word is not passed as much to the 100th word. Suppose you are considering the second word. The information of first word is passed into second word because it is very near. But if you are comparing with 100th word, the information is lost. This is called vanishing gradient. So this is the disadvantage of RNN, which have been overcome using GRU and LSTM. But if you're comparing with GRU and LSTM, the complexity increases. So you'll be having increased complexity. Okay, we are good. We are also having good GPUs, so we can think that we can also handle increased complexity. So it is better to use LSTM. But the disadvantage of all these is these are sequential. We need to find some other way in which we can process data parallelly in CNN style. So that's why they have introduced transformer networks. And if you see everything in this generation, like if you're having knowledge of Chat GPT, which uses GPT architecture, GPT-3 and GPT-4, and if you are seeing Google search engine, which uses BERT, so all these are based on the network transformer network. So it is in the paper, attention is all you need. From there, transformer took birth. Okay, let us get started. So this is a basic architecture of transformer network. Don't get tensed. I'll be teaching you step by step. The basic funda is we'll be giving inputs. We'll encode them. We'll be having an encoder layer. We'll be passing the information from encoder to decoder. Okay, let me draw it here. We'll be having an encoder block. We'll be having a decoder block. We'll pass inputs. We'll compute all the computation mathematical things. Just think it as a black box, and later on in this video I'll be teaching you how an encoder and how a decoder works. Okay, for now it's a black box. So it has made all the computations and it produced me two vectors or two outputs or any one vector. Okay, so this vector will be passed inside decoder and we will be giving a start of sentence token based on the information which it got here, and based on the tokens here, it will predict some output. We'll feed this output again to the decoder. Now see, we'll be having start of sentence as well as the word which is predicted. Based on the information which it got from the encoder, it will detect the next word. It goes on until we get end of sentence token. This is the basic idea of how transformer network works. Okay. See, here you have been given with positional encodings. I'll be telling you what is positional encodings. Okay, and we have multi-head attention, add and normalization, feed forward network, add and normalization, again masked attention, and all this stuff. Okay, let me tell you first what are the basic things in a transformer networks. Okay, first thing is we'll learn about positional encodings. What are positional encoding? Why it is needed? We'll be understanding self attention. What is self attention and what is attention actually? Next, we'll be understanding multi-head attention. What is multi-head attention and what all this stuff. Okay, and we'll be understanding add-on normalization. This is simply a residual block. See, if you are aware of a residual neural networks, let me explain you in image processing side. Suppose this is a dense layer. And if you are having 50 dense layers, the information gets lost because of vanishing gradient. So what we do is we will add this dense layer. We'll be skipping the connections. Like if you are having three dense blocks, we'll be adding the output of this dense block to this and this to this. We'll continue so that our information will not loss. Okay, the same thing we'll be doing here. We'll be adding and we'll normalize the data. Again, we'll send it to the encoder block. It continues for next times. You can choose. In the transformer networks they have chosen 6. You can also choose 8, 32, or any other number. It's of your wish. Okay, this is about encoder block. I'll be teaching you detail when I teach you encoder. Okay, now we'll be having masked multi-head attention, and you need to have, we'll be also learning about masks. What are different types of masks, like look ahead mask, and we'll be also learning padding mask. And then we'll be having multi-head attention, add and normalization, feed forward network, add and normalization, and linear dense network, and softmax. This is all about transformer network overview. I'll be teaching you in the upcoming videos, but for now I'll be just teaching you self attention and multi-head attention. So if you are aware of self attention networks in RNNs, it will be easy for you. Okay, for that you can also see my previous video on attention in RNNs. Okay, if you are not aware of that, I'll be teaching you from scratch. Okay, okay, what is self attention? Before that, let me teach you. And the other thing is, transformer networks is parallel way of processing data. Parallel way of processing data. So if you are having a very big input, this is a student. Unlike RNNs, we'll be passing this first. We'll predict output. We'll be passing this, and it continues. But in transformers, see, we'll be having this is a student. We'll be passing all this at the same time instance. So we'll be having parallel processing. And if you are aware, our GPUs are good at parallel processing. So transformer networks are comparatively fast. Okay. Let us understand about self attention and multi-head attention. Before that, let me teach you what is correlation. Suppose you are having a vector like this. I'm explaining it in mathematical terms. Then you'll be understanding easily. Suppose you have 2, 14, 2, okay, 12, and 196, and 1, 1, 2, and 196. Suppose you're having these numbers. Okay, let me just do matrix multiplication for all this. So if I do this, 2 into 1 plus 14 into 2, I'll get 30. 2 into 1 plus 14, I don't know this number, so let me write some big number like 10,000. 12 into 1 plus 196 into 2, let me take this as 400 or 4,000 just for sake of simplicity. 12 into 1 plus 196 into 196, let me take it as 1 million. Okay, so I got this vector. And if you are aware of CNNs and all those stuff, whenever you do max pooling, we'll be getting the feature which is 1 million. So let me bring the intuition here. Simply, whenever the numbers are very large, it weights more. Like it is responsible for feature detection. Like it is responsible. It acts as a main feature. Okay. And here, whenever you are multiplying 196 and 126, we got 1 million. This acts as a main feature. It affects. See, whenever you are using, suppose you are using a CNN or a dense network, so this will weigh more. A change in this will affect our neural network performance. Okay, and suppose you have 0 here. So if you are having a big number, now that if you are having a big number, it affects the neural network performance. Okay, so what is correlation? We are finding the relationship between different features. Like see, 196 into 1, we are finding the correlation. Like we got 196 into 1, sorry, 12 into 1 plus 196 into 2. So how much we got? 4,000. So correlation determines how much we are affecting the feature. Okay, You'll be understanding when I teach you Q, K, V matrices in self-attention. Let me clear the screen for now. Okay, erase all. Okay. Now, this is the formula for attention. Don't be tense. They'll be explaining you what is attention, what is Q, K, and V matrices. Before going into that, let me show you another example. See, I have an example. He is a student. Okay, computer does not understand strings, so we'll give this. He is a student in the form of numbers, right? So let me give you in the form of numbers. Like I'm giving four different number matrices. Like I'm giving four different number matrices. Okay, I have given four different number matrices. So what the researchers have made is they converted these matrices into three different matrices, which is Q, K, and V. How they formed Q, Q, and V matrices? They just multiplied with different weights. So let it be weight 1 matrix, weight 2 matrix, and weight 3 matrix. So they obtain Q, K, and V different matrices. Okay. Same thing QKV, QKV, and QKV. The intuition behind this, if you are aware of lookup tables, we'll be having a query and key and value pair. The intuition was that they also tried with different set of matrices. They used the four different matrices, three different matrices, or five different matrices. But they finally found that if you are taking three different matrices, the performance increased. Okay, let me show you those three different matrices Q, K, and V. So we are multiplying with some set of matrices W1, W2, and W3. We obtain Q1, K1, and V1. Next, what we are doing? So what we are doing is we are multiplying each query with the key. So if you are seeing here, see, we are multiplying Q1 and K1. We are multiplying, sorry, this is Q2, sorry, this is my mistake. Q2, V2, and this is Q3, K3, and V3, and this is Q4, K4, and V4. Okay, so we are multiplying Q2 and K1. We are multiplying Q3 and K1. We are multiplying Q4 and K1. Actually, why we are multiplying it? As I told you in the previous example, we are finding correlation. What is correlation? If it is high, it determines the feature. So what is correlation? It is simply a relationship between two different numbers or two different matrices. So we are finding the relation between he and is. See, if these two are related, I'll be getting high score, right? If these two are not related, I'll be getting less score, and in my probability distribution it will affect less. Suppose I write he is a student and next he has a book. So he here determines student, right? So student and he will be having higher correlation. So this is about correlation. Let me clear the screen once again. So we got Q, K, and V matrices. Next, what we are doing? See, as I told you, we need to perform correlation. So I am multiplying Q1 and K1, Q2 and K1, Q3 and K1, and Q4 and K1. The same thing I perform here, like Q1 K2. This is 2. I hope you understand. This is 3, and this is 4. So I'll be having Q1 K2, Q2 K2, Q3 K2, and Q4 K2. The same thing happens here, the same thing happens here. So in the form of matrix, they represented this way. We are multiplying a Q matrix with transpose of K. Q matrix will be Q1. Okay, let me erase this. Let me explain you it later. So we are multiplying. Okay, let me take my pen. So we are multiplying Q1 K1, Q2 K1, Q3 K1, and Q4 K1. We are adding all this and we are doing softmax. Softmax of all this. Why we are doing softmax? If you are aware of, if you are having a better understanding of machine learning and what is softmax, you will be understanding why we are using softmax. See, we are just simply adding all these terms to have one. That's why we are using softmax. After using softmax, now we are multiplying the value matrix. Okay, so we found the correlation between the first query and the first key. We are finding the correlation between different things and we are multiplying with the value vector and we obtain some other matrix. So this is called attention. Got it? And in order to normalize, we are just dividing the matrix by root of dk. So what is d? D is the dimension of embedding. Like suppose, let me clear the screen once again. Suppose I am taking the embedding size as 512 for example. I am representing he in 512 in the length of 512, like I am representing my embedding size is 512. So I multiply with different weights and I get q vector which is of size 512, v vector of size 512 and k vector of course of 512. Okay, let me write this as q, k and v. Okay, we are multiplying these two values and we are softmaxing the output and we are dividing it by root of dk. So what is dk? D is 512, so it is embedding size. And why only root dk? See, researchers have made different research. They use d square, d and every other thing, and they found that if we are normalizing using root dk, we get optimal results. So it's your choice. You can also use d square or any other thing, but the research found after many researchers root dk finds the best thing. Okay, and we are multiplying with v and we get the final output. So remember that you will be getting the same dimension as you provided here. So you got some other output and we'll be feeding it to the encoder layer. And this continues as I showed in the previous slide. Okay, let me show you what is multi-head attention. Okay, before getting started with multi-head attention, let me show you the diagram. You'll be having a better understanding. See, this was my Q matrix. I multiplied with the transpose of K. Simply we are doing Q1 K1, Q2 K1, Q3 K1 and so on. Like if I take this in the form of matrix, if you are having a better mathematical knowledge, you will understand. In this video, I will not teach you about the maths. Okay. See, this is the intuition. If you are seeing this image, you'll understand how Q, K are multiplied, how we are doing dot product, and why we are doing dot product as I told you in the previous video. This is about self-attention. See, this self-attention is also called scale dot product. See, if it to be precise, we are multiplying Q with K. We are doing matrix multiplication. We are scaling it by root dk, and I'll be explaining you about what is mask of different masks like padding mask and look ahead mask. Okay, for now ignore this. So we are matrix multiplication. We are multiplying it. We are dividing it by root dk. We are doing softmax, and again we are we are multiplying with v, and we finally get some output. This is called scale dot product. And as I already told you how we are getting v, k and q, we are having embedding size and we are multiplying with different weights. So in this way we get uh, q, k and v matrix and we found self attention. In the next video I'll be teaching you how to calculate multi-head attention. That's it for this video guys. Thank you.